There is an immense, largely invisible data architecture that is rapidly standardizing how modern engineering teams operate today. The metrics show strict, relentless momentum, over 16,000 commits and 13,400 stars on GitHub. This open-source repository is aggressively displacing heavily funded legacy enterprise data catalogs in active production environments. It specifically targets the most expensive engineering headache in modern infrastructure, the dangerous fragmentation of the data stack. Massive adoption stems from an urgent engineering necessity, closing the systemic blind spots created when teams attempt to manage data through disconnected silos. Picture the standard enterprise setup. Your team uses Amundsen for discovery, isolated Python scripts for observability, and static spreadsheets for governance. Then the catalyst event happens. An upstream engineer silently alters a schema type without notifying the downstream systems. The error propagates downward. Because the observability tool is walled off from the schema registry, automated pipelines break without triggering a single isolated alarm. The failure cascades until business stakeholders open their BI dashboards and find broken data before the engineering team even knows there is a problem. Engineers are then forced to spend hours doing forensic work, manually tracing the error back through these disconnected metadata silos to find the source. This diagram illustrates OpenMetadata's core thesis. On the left, an alert fails to cross the gap between isolated tools. On the right, a central repository intercepts the change and broadcasts it to all connected systems instantly. Treating metadata as separate applications guarantees systemic failure. Unifying it into a single operational control plane provides deterministic control. OpenMetadata achieves this centralized control by relying on 4 strict architectural pillars. This base layer, unified metadata schemas, establishes a common vocabulary. Above it, the metadata store acts as a central graph repository, mapping connections. Next, the API layer provides a standardized interface. Finally, the ingestion framework continuously pulls state data from external environments. Operating in tandem, these 4 pillars act as a control plane, giving you full lifecycle management from a single entry point. Standardizing schemas at the foundation ensures that as metadata scales, the definitions remain consistent across every connected application. Think of this framework as a central nervous system overlaid directly onto your existing data warehouse architecture, like Snowflake or dbt. The system utilizes over 84 native connectors to continuously query and map the precise state of these external pipelines. Skeptical. Legacy approaches rely on manual data logging or periodic batch scripts, ensuring the mapped state is always lagging behind the actual production environment. Continuous, connector-driven ingestion solves this, turning metadata from a static map into a live operational state repository. This live state powers the platform's most rigorous engineering capability, in-depth column-level lineage tracking. In this pipeline flowchart, you can track a single data column's exact transformation across the entire stack. This allows engineering teams to calculate the exact blast radius of a proposed schema change before they deploy it. But in complex enterprise deployments, heavily customized SQL transformations will inevitably break automated parsers. This UI represents the critical fallback, a manual drag-and-drop lineage editor. When auto-detection fails, engineers can step in and manually draw the graph. To maintain the health of these pipelines, a no-code data profiler lets teams build shared data quality test suites without writing custom evaluation scripts. OpenMetadata integrates tasks, webhook alerts, and notifications directly onto these lineage elements, making quality a shared workflow. Combining automated calculation with manual overrides provides a reliable audit trail for even the most complex data environments. We can validate OpenMetadata's architectural position by benchmarking it against existing market standards. While tools like DataHub prioritize a strict schema registry, OpenMetadata deliberately focuses its engineering on UI accessibility and collaboration workflows. Compared to Amundsen, OpenMetadata includes built-in data quality metrics and deep lineage tracking, moving it firmly past pure discovery. Recent GitHub commits show the team heavily optimizing Vite configurations for front-end code splitting to maximize UI speed. Simultaneously, a community is pushing for MCP OAuth support to establish enterprise-grade security integrations. This specific focus on front-end performance and secure authentication proves the community is building for enterprise-scale deployments, not just conceptual prototypes. But achieving this level of operational unification carries a heavy architectural cost. Supporting these unified features requires a highly complex multi-language server stack, a Java backend, TypeScript UI, and Python ingestion framework. Keeping this architecture running introduces significant compute and maintenance overhead. At scale, the underlying RDF metadata store faces latency limitations when ingesting massive data streams. Re-indexing this metadata store introduces noticeable latency when applied to petabyte-scale data lakes. Operating a trilingual, centralized stack requires dedicated platform engineering and a significant commitment to long-term maintenance. This leaves us with a serious architectural debate regarding the future evolution of the data management stack. If a centralized API-first metadata graph becomes the absolute enterprise standard, what happens to the ecosystem of standalone startups? Are niche, disconnected data quality and discovery tools destined to become obsolete features rather than standalone products? We review the architecture of tools like this every week to keep you ahead of the curve, so make sure you are subscribed. If you liked this breakdown, you will love our upcoming deep dive on Apache Superset. Click the video on your screen right now to watch that Superset deep dive, and thank you for supporting the channel.